Alright, welcome to page 3 of the notes, and we're going to talk about direction angles and direction cosines. And so what a direction angle is whatever vector that we have. So here we have vector A over on the right. Whatever vector that we have over there, it's going to be a certain degree measure. It's going to be angled away from each axis a little differently. And so if we wanted to determine, okay, what is the angle from the x-axis to our vector, that's going to give us, some type of angle, all right? And that angle is going to be alpha. If we want to determine, okay, what is the, direction, what is the angle from the y-axis, that's going to be beta. And whatever's the angle from the z-axis, well, that's going to be gamma, all right? And so what we're going to determine is, okay, given a vector, what is the angle measure from each axis? And so that's what direction angles are and direction cosines are. And so, again, I've given you all the Greek letters, alpha, beta, gamma, from x, y, and z. And again, these are going to be, in the interval between 0 and pi, just because of where they're located. I mean, if we had to go over, means that we probably should have went from the opposite side of the x-axis. So they're always going to be between 0 and pi, or 0 and 180 degrees. All right, so the cosines in these direction angles, so direction cosines are just basically, okay, cosine alpha, cosine beta, cosine gamma. All right, those are known as the direction cosine. So this is our direction cosine. All right, and how we can get that is we're going to take basically whatever our vector is A, we're going to take the unit vector of that, and so we're going to divide it by itself, and we're going to multiply that by just the, our term, whatever that is, in the first component of our vector. So that's why it's a sub 1 over a. So that means we're only taking our x value and dividing it by the distance of our vector. For cosine beta, we're going to take the second component, which is going to correspond to the y component, and we're going to divide that by the the distance of our vector. And the same thing for cosine gamma, we're going to take the z component, and we're going to divide that by the distance of our vector A. And that's how we're going to be able to determine, what our actual direction angles are. And in order to find the direction angles, we're just doing an inverse cosine everything. So starting off with example 6, find the direction cosines and the direction angles, and give the direction angles correct to the nearest degree. So for the first one, again, if you don't like it in standard basis vector form, again, you can say, okay, hey, we're dealing with a vector 1, negative 2, negative 3. So let's find our cosine alpha first. So cosine alpha is just going to be our a sub 1, so our x component, divided by the magnitude of vector A. So 1 squared plus negative 2 squared plus negative 3 squared, and that's going to give us 1 over the square root of, we have 1 squared, which is 1, negative 2 squared, which is 4, and negative 3 squared, which is 9. Add all that up and we get 14. So there is our direction cosine for alpha. And now what we want to do is let's go ahead and find the direction cosine for beta and our direction cosine for gamma. So now we just take the second component, or the y component, a sub 2, which is going to be negative 2, divide that by our magnitude of our vector, and we're done. And we're going to do the same thing with our third component, which is going to be the z component, divided by our magnitude, and we're finished. So those are the direction cosines. Now to find the direction angles, all we're going to do is and I'll change the color of this, we're going to define alpha, we just take the inverse cosine of our direction cosine, which is 1 over the square root of 14. We're going to do beta, and that's going to be inverse cosine of negative 2 over the square root of 14. And then we're going to do gamma, and that's going to be inverse cosine of negative 3 over square root of 14. And we're going to approximate all of these, and we're going to put them into, it asks again for degree, so we're going to put these in degree. And when we type these into our graphing calculator, we get 74 degrees, we get 122 degrees, and 143 degrees. Let me check to make sure that is 122 degrees. Just type it into my graphing calculator once more, because the way that I wrote it looks like it could be a 127. And so typing this into the graphing calculator, we get 122. All right. And so that's how we find direction angles and direction vector. And again, this is based off of right triangle trigonometry, and of how to find the cosine. The same way that what we're going to do next is going to be projections. We're going to talk about a vector projection and then a scalar projection, which is also going to be, could be called, a component of B along A. And so what the vector projection is say we have two vectors, vector A and vector B, and we're going along the line PQ, and what we're going to have is that there's going to be a projection of one of our vectors on top of another vector, and it depends on what we're asking for. But in this first instance right here, we have a vector projection of B onto A. All right, and be careful when you write this. When you write this, when we say we have a vector projection of B onto A, that means when we write it, we would write it, okay, projection, and it's going to be whatever we are doing, first like B onto A, so B's are bigger, letter A is going to be below that, so it's kind of like B onto A. All right, don't mess that up, because students mess that up all the time, so please don't do that. And so what a vector projection is okay, we have two vectors B and A, and the vector projection is wherever the terminal point of B, so the end point of our vector, however that makes a perpendicular line or perpendicular angle with our other vector, so vector A, the vector that's in between the starting point and wherever that point is on the vector, that right there is the vector projection. So we're projecting B onto A, so kind of like its shadow. So this is the vector projection. All right, it's just this vector, the length of this vector. All right. Now, scalar projection allows us to determine, okay, a scalar lets us know, how far we're actually going upon this vector. All right, and so the scalar projection is just the scalar of whatever vector that we're talking about. So it helps us give us, which direction that we're going. All right, so the scalar projection of B onto A also is going to be known as the component of B along A. That's defined to be, the signed magnitude of the vector projection. So it's going to allow us to have the distance, which is basically the number, the distance of B, the magnitude of B times cosine theta, so our angle in between, where theta again, is the angle between A and B. All right. There's a proof to this. If you'd like it, let me know. And I can go ahead and give you the proof of this as well.